Recording. Okay, so today is the beginning of a new book that we just finished the last one, and we're gonna talk about chapters 1 and 2 of this book.
I love this title.
Very modest, right? It's a book, not the book. Um, okay, we're gonna talk about chapter 1 and operations. I would like to have an honorable mention because in the beginning here, the author is specifically saying that he's gonna piss off the math people and go for intuition based teaching. I appreciate that.
Very nice.
Yeah, I'm so sorry, math folks. Yeah, it's part of life. Anyway, so now chapter one, why abstract algebra, right? And the line that I would like to draw today is that the way that this guy understands algebra makes me like reminded me of polymorphism,
Hmm.
and I'm gonna elaborate on that when we reach the portion of the text that reminded me of that. Anyway, so here he's kind of talking about chapter one is more about the history of the thing. Um, and then there's some portions that are very interesting to read, such as in elementary algebra. We learn the basic symbolism and methodology of algebra. We get to see how problems of the real world can be reduced to sets of equations and how these equations can be solved to yield numerical answers. Yeah. Uh, yeah, this is actually pretty interesting. So why algebra at the more advanced level is often described as modern or abstract, and it should be interesting to understand why that's called like that. So the first one about modern is kind of weird because this is very old stuff. So modern algebra is not very modern at all. So what about the abstract word? Yes, Mani?
I mean, it's modern relative to the rest of mathematics.
Well, I guess that's fair enough.
It's a bit like in the sense that modern music, when talking in the context of classical music, is not modern at all. It's like over 100 years old at this point.
Yeah, but this is 300 years old.
Oh, I mean, the fact that modern does not actually refer to contemporary, it's just
Yeah.
weird, but it's not uncommon used like that.
Uh, the abstract tendency in mathematics is a little like the situation of changing moral codes or changing taste in music. What shocks one generation becomes the norm in the next. And this is definitely true. So now we're gonna go through the whole history portion. And the funny thing about it is that we go about discovering how can we mechanically solve these type of equations. And I find it funny that there's so many background about this. Like I didn't know any of it. That's kind of interesting. Um, and well, this paragraph is essentially uh, describing that there's a bunch of new ideas that people found it weird in the beginning of the idea. So such this and the negative numbers and the complex numbers and things like that. And set theory also is in that bucket of like some very smart people in the past thought it was a silly idea and now everything's kind of based on that idea. That isn't to say that every silly idea in the past is not silly still, but some of the silly ideas we discovered it were not silly. Uh, okay, and now we're gonna go through the origin of things. So algebra, uh, uh, well, the word came from Arabic and was first used by this person who thought mathematics in this place during the 9th century. And
Baghdad.
the word may be roughly translated as reunion, as describe his method for collecting the terms of an equation to solve it. And there was also an understanding that this is a science of solving equations. Of course, later we discovered that this is not really. This is a simplistic understanding, it seems. Um, and then we go to the fact that methods of solving linear equations such as this one and the quadratic equation were well known before the Greeks, but then people had a hard time discovering the mechanical process to solve this one and to solve this one. I not gonna lie, I kinda already forgot the process. I learned it during college, but I have absolutely no recollection of it.
Cubic equations. Yeah, those are not something you see in high school.
Yeah. Um. Yeah, and then apparently, yeah. So there's a couple of sentences here that are interesting. So, um, uh, yeah, here those men who brought algebra to a high level of perfection at the beginning of its classical age were as colorful and extraordinary a lot as ever have ever appeared in the chapter of history. Arrogant, unscrupulous, brilliant, flamboyant, swaggering, and remarkable, they lived their lives as they did their work with style and panache. Is that
Panache.
panache?
Panache. That's how you pronounce it.
In brilliant dashes and inspired leaps of the imagination. Yeah, this is also something that the author says in the beginning, that he doesn't want the reader to understand algebra as like a mechanical, dead process, like dead and cold process. It is like a creative and imaginative endeavor. Uh, so he's gonna try to convince the reader of that. Um, and then the first character of this portion is Cardan, apparently, who was born in 1501. And then there's a bunch of like his background, like he did 2 graduations, things like that. Like it's again, people of the past, the bar was so much higher. Okay, that he had problems such as being a gambler, but well, people do have problems usually. Um, yeah, so he also needed mathematics. Okay, so he was also an astrologer, which is something that I do not encourage. But well, again, people are not perfect. But he was doctor, so that's cool. Um, and he was the one that actually found the general solution of the cubic equation. Actually, no, he was not that one, but it was discovered by this guy, Tartaglia.
Tartaglia.
Tartaglia. Um, yeah. And then the life of this second character was like turbulent, and it was like 1512. So again, very very old stuff. He and his father fled with many others into a cathedral for sanctuary, but in the heat of the battle, the soldiers massacred the hapless citizens even in that holy place. His father was
Not
killed.
cool at all.
Yeah, that was not cool. Um, yeah. Uh, he received no formal schooling, where he was a privilege of rank and wealth. However, he taught himself mathematics and became one of the most gifted mathematicians of his day. Again, the bar at that time was very different. He translated Euclid and Archimedes, and may be said to have originated the science of ballistics, for he wrote a treatise on gunnery, which was a pioneer effort on the laws of falling bodies.
Based.
And then he actually discovered the general solution for cubic equations. Well, without the X term, which is kind of a bummer. But then he kept that solution in secrecy. And there was another guy, a third character, that actually had the general solution for these type of equations. So without the x squared term, which again is kind of funny. It was agreed that and then they would have a competition. Right? They would have a contest, an algebra contest, which I have no idea what this means. Like, what is an algebra contest?
Well, they literally make up problems and give them to each other, and whoever gets the most problems correct wins. essentially.
Oh, okay. So this is not like a particular condition for winning. This was how this was done back in the day. Okay.
Yeah.
And then he solved the problems and actually finished the generalization of his solution. And the other guy didn't couldn't do any of the problems he settled. He chose for him to solve, and that should have been embarrassing, I imagine. But oh well. And then he kept his method for solving cubic equations to himself. Very known open source, very known open source approach. But in the end, he succumbed to Cardan's accomplished powers of persuasion, and then he promised to help him become artillery advisor to the Spanish army. He revealed the details of his method under the promise of strict secrecy, but then he got betrayed because the guy actually did publish the method, even though he uh, gave the original author the full credit. That was not enough. A bitter dispute arose between the mathematicians. And then I don't know what this sentence means, from which he was perhaps lucky to escape alive. So a dispute was violent dispute. It was not a legal dispute.
No, it was violent. Those were different times, Lemos.
Okay, but why is the word chosen here dispute? Like this doesn't give the sense of violence at all, but then this sentence kind of does. He lost his position and then vanished. And the next great step in the progress of algebra was made by another member of the same circle, and then it was the guy that discovered general method for quartic equations. So probably even more boring. Uh, he learned Latin, Greek, and mathematics. He won fame after defeating the guy that made the cubic solution in the context in 1548 and received an appointment as supervisor of tax assessments in Mantua. This position brought him wealth and influence, but he was not able to dominate his own violent disposition. Man, again, I don't understand. Like, math? Like, people are having wars because of math? Like, what are we doing?
I mean, this is basically Yu-Gi-Oh! In real life.
He quarreled with the regent of Mantua, lost his position, and died at age 43. Tradition has it that he was poisoned by his sister. Very tragic. Um, 10 years later, Cardone was arrested for heresy because he published the horoscope of Christ's life. He spent several months in jail and was
Wait, you
released.
skipped a line. Cardenson poisoned his unfaithful wife and was executed. Like, what is with people and poisoning people at that time?
I mean, but it is just like twice. Like I'm more interested in the part of people are violently beating each other because of math. That's the portion that I have yet to understand. Uh, he spent several months in jail and was released after renouncing his heresy privately, but lost his university position and the right to publish books. He was left with a small pension, which had been granted to him for some uncountable reason by the Pope. Again, what's going on with this like characters that participate in these stories? Um, it became clear that methods can be solved to many different types of equations. Formulas had been discovered which yielded the roots of all cubic and quartic equations. Now the challenge is to go higher, a degree higher than 5 or higher. During the next 200 years, there was hardly a mathematician of distinction who did not try to solve this problem, but none succeeded. Progress was made in new parts of algebra, and algebra was linked to solve with the invention of analytic geometry. But the problem of solving equations of degree higher than 4 remained unsettled. It was, in the expression of Lagrange, a challenge to the human mind. Yeah, but this again, I'm not saying we should not praise the people that discovered the general solutions to solve these type of things, but it's boring as AF, man. Um, it was a great surprise to all mathematicians when in 1824 the work of the young Nigerian prodigy named Abel came to light. In his work, he showed that there does not exist any formula for the roots of an algebraic equation whose degree is 5 or greater. This sensational discovery brings to a close what is called the classical age of algebra. throughout the age of algebra was conceived essentially as the science of solving equations, but it's not like that anymore. Anyway, uh, and nothing too crazy here. And now we actually go to see some definitions. So if you have a matrix is a rectangular array of numbers such as this one. And we actually use this as a way to encode the information contained in a system of equations. And this is called a matrix of coefficients. Um, since the solution of this pair of equations depends only on the coefficients, we can essentially remove the noise. And we can also talk about the matrices arranged in rows and columns, such as these rows and these columns. And we can also, and there are rules based on the size of the, like how many rows and columns you have in the matrix. So if you have a 2 by 2 matrices, and then you have this addition operation, this is the zero matrix, and there is also the dot product of vectors. Um, and then when you apply dot product operation on matrices, there's like these schematics here that you apply this formula for each of the combinations of rows and columns of the two matrices. So if you have the row of this and the column of that one, you have the 5 and so on and so forth. You always grab the row of the former, the first, and the column of the latter. And this will lead us to the conclusion that is not commutative, which is, well, I guess it is kind of weird because up to the point that you learn matrices, I believe everything is commutative.
Uh, yeah, you typically don't learn quaternions at that point. Actually, I'm pretty sure people don't learn quaternions until they are well into university.
I'm
Um,
sure they don't learn quaternions even at the university. They only learn them when they're doing games.
but yeah, basically, even if you go all the way up to complex numbers, multiplication is commutative until that point.
Yeah, and matrices and kind of introduce this weirdness. And there's also the problem of like some of the invariants that you are usually not noticing, but you actually base your some assumptions on those invariants. They also don't they stop holding, such as a squared equals 0, then necessarily a is equal to 0. That's not true for matrices. There's also the problem that you if you have AB equals AC, um, then what is this? The name of this? It's not transitivity, right? But there is a name for this type of property that I don't remember right now. But in
Uh,
algebra, this doesn't hold. B is not necessarily equal to C. Yeah?
yeah, I don't recall the name either.
Yeah. Then, uh, the identity matrix is like this, and you kind of don't know why it needs to be like this. Like this diagonal in particular is very important. Um, it took me a while to have an intuition of why this needs to be like this. And then if a yeah, and there is also this other invariant that if a squared equals to 1, may be minus or plus 1. But again, matrices break this rule. Um, and then yeah, because in here can be identity or well, it is not, right? So if you have a times a matrices, the outcome is going to be identity. But this doesn't mean that a is either identity or minus identity. And why? Okay, so this is essentially one algebra. We haven't seen what the definition of algebra yet because it's kind of chapter 2. But, well, end of chapter 1 and chapter 2. But this is essentially to say that there's like algebras that essentially break our intuitions of some properties that we are usually assuming to hold. And then you go to another algebra called the Boolean algebra. That, well,
I'm not a
okay,
fan.
you don't like Boolean. Oh, you don't like Booleans, but you also don't like the algebra. Is that what you're saying?
I'm okay with the algebra. I just don't like booleans.
Yeah, I'm very fine with Booleans. I don't have any grudge against them. Uh, but they do hold these properties, right? So what is this? This is saying that plus is commutative and times is multiplications is commutative. Times and plus and sum being like union and intersection, assuming that S is that A and B are sets, right? And there's also distributivity, and there's also identity for the addition and identity for the well multiplying by empty set gives empty set. But then the Boolean algebra also adds these operations here that are not actually analogous to elementary algebra. Because a plus a is equal a, and that's kind of weird. And a times a is also equals a.
Yeah.
And the sum and the plus are like they can switch places with this one and this one. And the distributivity, if the plus is on the outside, also kind of gets kind of weird. So this unusual algebra has become a familiar tool for people who work with electrical networks, computer systems codes, and so on. It is as different from the algebra of numbers as it is from the algebra of matrices. And then there's more examples such as the complex and hypercomplex algebras of vectors and tensors, and many others. And then it's essentially the same kind of situation as programming language. There are many, many of them, and nobody really
Yep.
knows the like. We're still debating about the best ones. And now we are actually talking algebraic structures. Okay, so science of solving equations is not cutting anymore. It's not cutting. So it had to be viewed such as more broadly as a branch of mathematics capable of revealing general principles which apply equally to all known and all possible algebras. Right. So this is the beginning of the hint that I had. Okay, what is also trying to pull this off? Like polymorphic functions. You have a type, and you have a function that works with many types. Doesn't really matter the type. It does only matter that some operations are being held. So this is why I said, well, this is only one piece of text. There's more. We're gonna go through more examples when we talk about rings and things like that. But I kind of reminded me of like polymorphism type classes, things like that. What is it that all algebras have in common? What trait do they have which lets us refer to all of them as algebras? In the most general sense, every algebra consists of a set and certain operations on the set. An operation is simply a way of combining two elements of the set to produce a unique third member of the same set. We're going to see more about this in chapter 2. Thus, we are led to the modern notion of algebraic structure. An algebraic structure is understood to be an arbitrary set with one or more operations defined on it. An algebra, then, is to be defined as a study of algebraic structures. It is important that to be awakened to the full generality of the notion of algebraic structure. We must make an effort to discard all our preconceived notions of what an algebra is and look at this new notion of algebraic structure in its naked simplicity. Any set with a rule for combining its elements is already an algebraic structure. There does not need to be any connection with known mathematics. For example, consider the set of all colors and the operation of mixing any two colors to produce a new color. This may be conceived as an algebraic structure. It obeys certain rules, such as commutative law. In a similar vein, consider the set of all musical sounds to create other combinations of sounds. We can also apply this rule to people, and the rule having the closest common relative of any two persons present at the reunion. These two is an algebraic structure. We have a set and an operation on that set. As the general notion of algebraic structure became more familiar, it was bound to have a profound influence on what mathematics perceived algebra to be. In the end, it became clear that the purpose of algebra is to study algebraic structures and nothing less than that. Ideally, it should aim to be a general science of algebraic structures whose results should have applications on particular cases. Before we take a look, we must briefly examine other aspects of modern mathematics, namely the increasing use of the axiomatic method. And then it glazes Euclid's elements all the way. I'm not saying that's an unfair thing to do, but like And again, it's kind of true that it's kind of awesome that the guy pulled that off with a very like with this axiomatic method, and he actually popularized the use of this method for future generations. And then now he's talking about that this was very like it was a breakthrough moment because apparently people were not really understanding things like that because mathematicians consider logical demonstration to be an auxiliary process like the preliminary sketch made by artists, a private mental process which guided them to a result but did not deserve to be recorded. And here's a hot take about this though. Am I disagreeing that the method used to reach a certain demonstration to reach a certain conclusion is not important? No, it is important. But I do believe that even if you do it like that, that's not the I classify intuition of some demonstration to be more important than the demonstration itself.
Hmm.
Because here's the thing. At the moment that you don't know how, like, you don't know what's happening, you're just following a mechanical process, you actually don't know the meaning of any of it, right? So at the moment that you are literally just following a recipe book of doing some transformations on a piece of text, uh, you lost the capability of understanding what actually is happening with those transformations. And that's why, again, I'm not saying we should not praise the demonstrations. We should. But I also think that they were not necessarily like wrong on like considering other aspects as the big deal of it. As also a big deal, I should say.
Hmm.
Because in my experience, if I know how to do something mechanically and I don't know the intuition of it, and I don't really know what it means, then I'm bound to forget about it very shortly after I have it. And I am bound not really remember that this is in my toolkit that I can use in a paint in if I have to.
Right, where if you actually have the intuition, even if you forget the details of how to execute it
Exactly.
mechanically, you can just rederive them.
Not only rederive them, but if you have an intuition, it kind of becomes like, oh, this problem fits this principle. I don't remember the the steps to mechanically use this principle effectively, but that you can look it up. You can look into the internet, you can look in a book. But if you don't have the intuition, then the pattern matching to identify that the problem fits the method, the approach fails. And then it doesn't really matter that there is a mechanical process because you don't know it, you forgot about it. So the intuition is important because it allows you to do pattern matching on the available ways to solve a problem that you know with the identifiable properties of the problem. And that's to me really, really important. Like really, really important, in my opinion. That's how the Eureka moments happen to me. Um, it is also known today that many of the geometric theorems in Euclid's Elements came from more ancient times and are probably borrowed by Euclid from Egyptian and Babylonian sources. However, this does not detract from the greatness of his work. Important as are the contents of the Elements, what was proved far more important for posterity is the formal manner in which Euclid presented these contents. The heart of the matter was the way he organized geometric facts, arranged them into a logical sequence where each theorem builds on preceding theorems and informs of the logical basis for older theorems. Um,
Yeah, this parenthesis here is very, very relevant.
yeah, we must carefully note that the axiomatic method is not a way of discovering facts, but of organizing them. New facts in mathematics are found, as often as not, by inspired guesses or experienced intuition. To be accepted, however, they should be supported by proof in an axiomatic system. Yeah, I have a question though about this parenthesis. Does this mean that if I reach a conclusion using the axiomatic system method, and I reach a conclusion that is not yet not known, that's not a fact. Is this what this is saying?
No, it's just not accepted fact. There's a distinction there.
No, no, no. It is
Ac-
accepted because I use the axiomatic system to reach it. But it's
Hmm.
not based on guesses or experience intuition at all. I was just mechanically applying the rules.
Well, that would be a corollary.
Exactly. But is that corollary a fact then?
Well, yes.
So it
Well,
is it
assuming
is a
that
way of
as
discovering facts.
well, assuming that the axioms are true, right? Because they may not be.
Sure.
But if they are, then well, a corollary is a logical implication of existing axioms and theorems derived previously from those axioms, so it is true
Yeah,
as well.
yeah, so this parenthesis is kind of misleading because you can actually discover facts with it.
You can, but is it a good way of discovering facts that are not obvious in retrospect from the system?
Wait, repeat the question.
You can discover facts from it, but it might be implying that it's not a good way of discovering facts that are not actually obvious from the surface characteristics of the system that you're using to discover the facts.
I don't know about that one. Like you were saying that a corollary is trivial then. Are you saying that?
In a certain sense, yes. That think what the paragraph is trying to say is that if you want to discover facts that are about a system that are not necessarily trivial, then more more often than not, you need some leap of intuition or some education that guess, and then try to work backwards from that guess to try and formalize that into an existing system, rather than trying to derive that from the system itself.
I agree with the what which with what you said at the end. I just don't think I agree that every corollary is immediately trivial. I think there's many examples of this happening that like the same axiomatic system took like decades or centuries for somebody to actually found a corollary that nobody found before.
But usually that person who found it didn't work by deriving from the system. They had an intuition and then they worked backwards.
No, yes, but it was in the system. He just could not see it, but it was already there. You could say, right? He didn't found a new system. The axiomatic system was always there. Everybody was looking at it, but everybody couldn't derive it. And I think saying that every corollary is trivial kind of diminishes this eureka moment that, oh my god, there it was always there. I was just blind. Anyway, Euclid's elements have stood throughout the ages of the model of organized rational thought carried to its ultimate perfection. Mathematicians and philosophers in every generation have tried to imitate its lucid perfection and flawless simplicity. Yeah, I haven't read Euclid's Elements, so I don't really know how fair of this glazing is. I know it's important, of course. I just don't know how if saying that it's lucid perfection and flawless simplicity fits. I don't know that. So there are some philosophy and math people. They dreamed of organizing our human knowledge into an axiomatic system. And then there's another person that created a deductive system of ethics patterned after Euclid's geometry. While many of those dreams have proved to be impractical, the method popularized by Euclid has become the prototype of modern mathematical form. Since the middle of the 19th century, the axiomatic method has been accepted as the only correct way of organizing mathematical knowledge. To perceive why the axiomatic method is truly central to mathematics, we must keep one thing in mind. Mathematics, by its nature, is essentially abstract. For example, in geometry, straight lines are not stretched threads, but a concept obtained by disregarding all the properties of stretched threads except of extending in one direction. Similarly, the concept of geometric figure is the result of dialyzing from all the properties of actual objects and retaining only their spatial relationships. Now, since the objects of mathematics are abstractions, it stands to reason that we must acquire knowledge about them by logic and not by observation or experiment. This is really important, this sentence here, that it is an abstract process because we are purposely ignoring some of the properties of the objects that we are interested in and just retaining the properties that we actually care, which is also something that reminded you of type classes and polymorphism. Because usually you don't really care about the meaning of any implementation. If you have the minimum requirements for a type class, you are done. It doesn't really matter if it makes sense or not. So I'm kind of spoiling because we haven't reached that part of the text yet. The notion of algebraic structure is obtained by idealizing from all particular concrete systems of algebra. We choose to ignore the properties of the actual objects in a system of algebra and return our attention simply to the way they combine under the given operations. In fact, just as we disregard the objects in the system R, we also disregard what the operations do to them. We retain only the equations and inequalities which hold in the system, for only these are relevant to algebra. Everything else may be discarded. Finally, equations and inequalities may be reduced from one another logically, just as spatial relationships are reduced from each other in geometry. That's what I meant, right? So everything is like, we actually stop asking if this makes sense and we just apply the operations. This is also something that reminded me of like polymorphism in type classes. It's kind of I also do the same when I'm doing those things. Um, and then the axiomatic of algebra. So now I'm going to list a couple of properties, well, a couple of equations that are interesting in general. We assume that A is any set and there is an operation on A which we designate with the symbol asterisk. And then A asterisk B is equal to B asterisk A. If this equation is true for any two elements, we say that the operation is commutative. What it means, of course, is that the value of this and this is independent of the order in which A and B are taken. And in equation 2, which is associativity, remember that an operation is a rule of combining any two elements. So if you want to combine three elements, we can do so in different ways. If you want to combine A, B, and C without changing their order, we may combine A with the result of combining B and C, which produces this distribution of parentheses, or we also have this other way. The associative law asserts that these two possible ways of combining three elements yield the same result. And then we have the identity element equation. An identity element is sometimes called a neutral element, for it may be combined with any element A without altering A. And we have 0 for addition and 1 for multiplication. And finally, the inverse. So it's the act of applying the operation of something and the inverse of something and getting the identity. We say that every element has an inverse with respect to the operation. The meaning of the inverse should be clear. The combination of any elements with the inverse produces the natural element. And then we have A and minus A. And we also have multiplication, assuming that A is not equal to 0. And then finally, we have, let us assume now that the same set A has a second operation, symbolized by bottom, as well as the operation asterisk. So now we have this equation here. And then if this equation holds for any three elements, we say that asterisk is distributive over bottom. If there are two operations in the system, they must interact in some way. Otherwise, there would be no need to consider them together. The distributive law is the most common way for two operations to be related to each other. Cool. Okay, so again, these equations are kind of like disregard of what the set actually is and what the members are.
And also what the operations actually do.
Yeah, and what the operations mean. It's very polymorphic in this sense. It doesn't matter. It also reminded me of the category theory book, Marinho.
Yeah, basically you don't care about what those things concretely are. You just care about how they relate to each other.
Yeah, exactly. There are other basic laws besides the 5 we have just seen, but these are the most common ones. The most important algebraic systems have axioms chosen from among them. For example, if you have a ring, the mathematician is referring to a set A with two operations, usually symbolized by plus and multiplication, having these axioms. So addition is commutative and associative. It has a neutral element commonly symbolized by 0, and every element A has an inverse minus A with respect to addition. Multiplication is associative, has a neutral element 1, and is distributive over addition. Matrix algebra is a particular example of a ring because it has all of those equations holding there. However, there are many other examples of rings: numbers, functions, words, switching components, and a great many more. Every algebraic law which can be proved in a ring is true in every example of a ring. Again, it reminded me so much of type classes, this thing. In other words, instead of proving the same formula repeatedly, once for numbers, once for matrices, once for switching components, and so on, it is sufficient nowadays to prove only that a formula holds in rings, and then, of necessity, it will be true in all the hundreds of different concrete examples of rings. So it's kind of the same problem that programmers have with boilerplate code. They also found the same problem, but years ahead of us. Sure. By varying the
now that
possible, go on.
now that we're going over this, that actually makes me wonder. Does Prolog form a ring, like with the and or in the composition?
I don't have a clear picture of what you're saying right now in my head,
Well, actually, not even
but
Prolog specifically, but I guess it would be easier to think about a concatenative language because then you just care about the compositions. Because like you have let's use for as an example. You have composition of functions, which is associative, right? You typically don't have an inverse for that for composition, but some dialects do. Like factor, there is actually a way to get an inverse for a function, and you can build a system where every function has an inverse, so that's possible.
yeah, but what is
Um,
addition and multiplication in that?
well, addition would be function composition, and then multiplication would be disjunction, actually.
What does it mean to have disjunction in a concatenative language?
That means you have a function which is composed of two other functions, and the result of applying it is the result of applying either of the functions that it is made up of. So it's kind of like an OR. And typically you don't have that directly. You usually have an if, right? But an if is just a disjunction with an implicit negation in one of the branches.
Um, okay, is that stuff disjunction distributive over the composition?
Yeah, that's what I was wondering actually, because I think it might be, but I haven't looked into it. It's just an idea that I literally just had.
Now, it wouldn't surprise me if that's the case, because again, this is a bunch of properties. This is actually like defining something based on its properties, and that kind of goes into a whole philosophical debate that defining the properties of something is not describing the something. But for the sake of this book, I think sure, I wouldn't be surprised if concatenative languages are rings.
Well, they are at least monoids. The question is whether they have enough properties to have additional structure, right? And that will obviously vary depending on the language that you're considering. But yeah,
Uh, by varying the possible choices of axioms, we can keep creating new axiomatic systems of algebra endlessly. We may well ask, is it legitimate to study any axiomatic system with any choice of axioms, regardless of usefulness, relevance, and applicability? There are radicals in mathematics who claim the freedom for mathematicians to study any system they wish, without a need to justify it. However, the practice in established mathematics is more conservative. Particular axiomatic systems are investigated on account of their relevance to new and traditional problems in other parts of mathematics, or because they correspond to particular applications. Yeah, I'm very worried about this, because here's the thing. If you don't have the radical people exploring things that nobody's willing to explore by themselves, I have a feeling this threatens innovation. I really do. Because if this doesn't happen, this means that any new encountered problem, we're going to try to force it to fit in any of the conservative and well-established axiomatic systems already being used. And if you think about it, the only reason we have functional programming is because of the radicals. Like, the more conservative and well-established player is like descendants of Turing machines. Uh, so I really think that okay, this is a fair description of the radicals, but I think it should have like said that they may be crazy, but they matter. Like that should have been said, in my opinion. In practice, how is a particular choice of algebraic axioms made? Very simply, when mathematicians look at different parts of algebra and notice that a common pattern of proof keeps recurring, and essentially the same assumptions need to be made each time, then find it natural to single out this choice of assumptions as the axioms for a new system. It is exactly how we, as programmers, do our polymorphic shit. Isn't it? Same thing.
Well, that's just how you do abstraction in general, no?
Um, well, yes, but I think the parallels are true. Like, the decision-making process is also the same thing. You can say that, oh, making abstractions also follow the same thing. Yeah, but we're in the context of being programmers, right? So that's why I want to try to make that bridge. I was not expecting to find a bridge so fast in reading a math book. Uh, Another important aspect of axiomatic mathematics is this. When we capture mathematical facts in an axiomatic system, we never try to reproduce the facts in full, but only the side of them which is important or relevant in a particular context. This process of selecting what is relevant and disregarding everything else is the very essence of abstraction. And here's the thing, like to summarize all of this text here. We the same object can be analyzed from different perspectives, which may be in different systems, algebraic systems. So you have numbers, for example, and then they form a ring, but they also form piano numbers, but they also form other things. They can all be the same at the same time. They can all be those things at the same time. That's what I meant to say. So it's a reality with many facets. So you have the ring interpretation. We have. It's also the same thing about the whole S expressions and homoeconicity thing. You can think that is only a funny syntax that you are rearranging the parentheses, but you can also think that it's a way to express your code as a bunch of data structures. Both interpretations are valid, but they have their use cases and their usefulness in different contexts. Um, yeah, so no longer are the integers one subject, complex numbers another, matrices another, and so on. Instead, particular aspects of those systems are isolated, put in axiomatic form, and studied abstractly without reference to any specific objects.
Hello, Ace.
We can't hear you, my friend. Am I the only one not hearing Ace?
I can't hear him either.
Okay. Um, and then we have Galois, which has a very tragic story, as far as I remember. And it was very hard to, and he was unfortunate enough to have his stuff published only 15 years later after his death, which must be very frustrating, man. You know you have something that people are worthwhile people's time, but you are having a hard time sharing that stuff, and then you die, and then 15 years later they recognize what you're saying. Tragic.
Yeah,
And
and the way that he died too. You know the story?
Sorry, Ace.
The way that he died. Do you know the story?
I don't actually.
well, it's written
Okay, so
here.
Well,
oh,
yeah,
is it?
I think it is written here.
Yes,
It
it
was
is.
over a
Okay,
duel,
okay.
right? Yeah, again, What's up? What's up with those people, man? Like, the
Yeah,
math
over
people
over
were
a lady.
violent. Well, what's going on? Like the whole story of the people discovering the general solutions for system of equations of different degrees. There was also violent in those. Like, what's going on?
Those were different times, Lemus.
No, no, no. I understand, but we're not going to cave times. We're going to like ninth or 10th century. You know?
Well, actually, it's the 19th or 18th century, and this is not really
Because of
cave
that,
times
why? Yes.
because he was killed in a duel. It was a civilized form of violence.
Okay, I don't understand what's up, but okay.
Yeah, very sad.
Uh,
He was sent to the Shadow Realm before his time.
Algebra today is organized axiomatically, and such it is abstract. Mathematicians study algebraic structures from a general point of view, compare different structures, and find relationships between them. This abstraction and generalization might appear to be hopelessly impractical, but it is not. The general approach in algebra has produced powerful new methods for algebraizing different parts of mathematics and science, formulating problems which could never be formulated before, and finding entirely new kinds of solutions. Yeah, and this is again saying the thing that I said before. Mathematicians study structure independently of content. So this is really important because this means that we don't actually like we put the meaning of things afterwards. And that is very okay. This is again a hot take. Here's my hot take. I think engineers need to be more a little bit more like that. Because in my experience, when I did my masters of like doing math, I witnessed a bunch of other engineers like afraid and anxious, high levels of anxiety, because they could not understand immediately or form any intuition immediately about the math subject. And I was kind of fine because I've seen that math content before, so I already had an intuition in my mind, and I had to help them through the exercises and stuff. But you need to be more like open of like study the structure regardless of the content. Cool. And now we're actually going to talk about operations, which believe it or not, it's more complicated than I thought. So an operation asterisk on A is a rule which assigns to each ordered pair of elements of A exactly one element, the result of the operation on the pair in A. And then let's go pedantically over some parts of this definition. So the first thing is that A asterisk B is defined for every ordered pair. There are many rules which look deceptively like operations but are not, because this condition fails. Often, A asterisk B is defined for all obvious choices of A and B, but remains undefined in a few exception cases. And then, of course, we're going to bring up the division by zero case. Because if you apply such division, you cannot, for every ordered pair, go back to have an outcome that is present in the original set of the elements. In this case, it could in reals, but it could be in another set. That's fine, like integers. A asterisk B must be uniquely defined. So in other words, it cannot be ambiguous. So that's the same thing with like true operation 8, because maybe it's going to be 4 or minus 4, and then that's ambiguous. So that's a very important thing to remember. And then if A and B are in the set, then again their outcome must also be in the set, which means that the operation is closed. The operation that A is closed under such operation. If we propose to define an operation asterisk on a set A, we must take care that asterisk, when applied to elements of A, does not take us out of A. And again, this goes to the whole thing about, okay, if you have 3 and 4 and you are in naturals, the this division gets us out of naturals, for example. On the other hand, yeah, and there's the more example of the division. An operation is any rule which assigns to each ordered pair of elements of a unique element in A. Therefore, it is obvious that there are in general many possible operations of a given set A. And then we have this table here that we can have all the possible combinations of ordered pairs. So A, A, B, B, A, and B, B. and then we can do the 16 possible outcomes in the operation.
Well, this
Uh,
is a finite domain with just two elements, so it's isomorphic to booleans, unfortunately.
of course. Each of these tables describes a different operation on A. Each table has 4 rows, and each row may be filled with either A or B. Hence, there are 16 possible ways of filling the table, corresponding to 16 possible operations on the set A. Yeah? And then we have the commutative property that we've seen before. Is expressed like this. We have associativity expressed like this. And then it's repeating the same thing. I actually don't mind repeating it, especially for people that are not used to it. Because again, associativity is a way to express a rule about the different ways of combining three elements. And because we have only binary operators, we have to then associativity actually matters. So it's the same thing as we read before. And then another example that this does not hold. If there is an element E in A that we have this property, so this is the neutral element. We've seen this before. Uh, and then equation 3 tells us that when E is combined with any element A, it does not change A. And for example, in the set of reals, A 0 is neutral and 1 is neutral, but for different operations, right, such as addition and multiplication. And then we also have the inverse, right? So another operation. So we're essentially grabbing the properties that we read in chapter 1 and like using them to talk about operations. And then if you apply the operation of an element with its inverse, we get the neutral element. And then we have A with minus A, and the same thing with 1 divided by A, assuming that A is not 0 for multiplication. And we usually use this symbol to denote the inverse. And just a side note, inverse of matrices are boring AF to make. And of course, there are rules for 2 by 2 and 3 by 3 matrices, but holy damn, I remember that after that it gets really, really, really boring. And then we have exercises, and then finally, beginning of chapter 3. Okay, so any comments? We have 57 minutes.
Yeah, this is a nice book so far. Also, the Renaissance was violent.
Yeah, no, I
So
still go on, Ace.
So I think after the first few chapters, we'll definitely want to go through some of the exercises. I mean, the first few chapters, the exercises are going to be trivial, but later when these chapters get more in depth, I think the exercises are going to be valuable for us.
Okay, that's good to know. That's good to know. Okay, so what are we settling for next time? Um, so there's chapter 3. It's very sad that there's no pages in the summary there. So this is what, chapter page 31 goes all the way to... Oh wow, there's actually more exercises than text in this one. Yeah, so we're definitely going to do chapter 3 in its entirety. Elementary properties of groups. 41, 44. Okay, the chapters are really tiny, and there's actually more exercises than theory to read.
That's what I was getting at, yeah.
Yeah, so Ace, do you know if the exercises of chapters 3 and 4 are worthwhile?
I mean, so they're definitely going to be a little bit more challenging, and yeah, I think we should go through some of them for chapter 3 and 4. Maybe not all of them, because I mean, maybe some of them are a little bit too trivial, but yeah, I think like I said, the further on we get into the book, the more worthwhile they'll become.
Okay, so in that case, do you think we should like only do chapters 3 and 4, considering the exercises, or we should try to go with 5 as well?
What's
For 1 hour.
5?
5 is
Well,
subgroups.
ooh,
Yeah, subgroups.
I think probably
Oh,
3 and 4
the
makes
balls and the
sense.
arrows. The balls and the arrows, folks. Every time. You just have to wait a little bit, but the balls and the arrows always come back.
Yeah. Can never get away from category theory.
Yeah. Okay, so you think for 1 hour is chapters 3 and 4?
Yeah, I think so. Especially if we're going to go through some of the exercises. Yeah.
Yes,
Yeah,
buddy.
like look at that. It's asking you to like list out like all the elements, write an operation table. So yeah, that will definitely take some time. I don't think we have to do all the exercises, but let's pick a couple of the exercises and work through them. I think that'd be worthwhile.
Okay. Yes, money.
The balls and arrows never left Lemos. You are a programmer. You deal with graphs every day, even if you don't think about them.
Well, I mean, pedantically, you were right, but I'm more talking about noticing them. Because I was just scrolling, waiting for them, and in chapter 5, there they are. There they are. Anyway, so we're gonna do chapters 3 and 4. Tevo, do you agree with this assessment for next time?
Next time you mean the next 1 hour, or do you mean
The next 1 hour,
next week?
which is
The
next week, yes.
the next 1 hour in the
Oh,
next
okay.
week.
That makes sense to me. That's fine.
Okay, so I'm gonna finish the recording now.